You know, when you pick up a handful of sand at the beach, you are basically holding the foundation of the entire modern world. It slips through your fingers, it gets stuck in your shoes, it seems, completely unremarkable.
Yeah, it's just dirt to most people.
Right, just dirt. But take that exact same sand, run it through one of the most extreme, mind-bending manufacturing processes ever devised by human beings, and it becomes the brain of the smartphone sitting in your pocket right now.
It really is the ultimate alchemy when you think about it.
Exactly. To understand how we do that, how we use harsh chemicals, extreme heat, and invisible light to bend atoms to our will, is to understand the absolute foundation of the modern digital reality.
Because it's everywhere.
Everywhere. Every system you rely on, from global finance to artificial intelligence to the anti-lock brakes in your car, depends entirely on our ability to mass produce these microscopic circuits with zero margin for error.
Okay, let's unpack this because to make a microchip, you have to start at the very beginning. And that beginning is literally dirt. Like I said, alchemy. The core raw material for all of this is silicon, which we extract from silicon dioxide, which is essentially just sand.
But you can't just throw a bucket of beach sand into a furnace and expect a computer chip to pop out, right?
Oh, definitely not. First, we have to purify it to a level that honestly barely even exists in nature.
Right. I was trying to wrap my head around the scale of the purification here. It involves a chemical distillation method called the Siemens process.
Yep, the Siemens process.
And the goal is to achieve what is known as electronic-grade silicon. And the required purity is 99.9999999% pure. 9 nines.
It's hard to even conceptualize that. To put 9 nines of purity into perspective, imagine you have a billion atoms of silicon.
Okay, a billion atoms.
Out of that entire billion, you were allowed exactly 1 atom of an impurity, maybe 2.
Wow. Just 1 or 2 atoms.
Right, because at the atomic scale where these circuits actually operate, even a single stray atom of like carbon or iron can throw off the electrical behavior. It would completely ruin the final chip.
So we use this intense chemical process to achieve this absurd pristine level of purity. But then we're just left with pure silicon chunks, right? And we have to form it into a unified structure.
Exactly, using something called the Czochralski process.
Right, and from what I understand, we melt this ultra-pure silicon in a crucible at roughly 1420 degrees Celsius. Then we dip a tiny, perfect seed crystal into that glowing, molten silicon and very, very slowly pull it upward while spinning it.
Yeah, it's a very delicate pull.
And this forms a massive single-crystal cylindrical ingot. Like, it can be incredibly heavy and several feet long. But I have to push back here. Why is this tedious single crystal pulling process so intensely necessary?
Well, it's about the crystal lattice.
Because if we just need flat, pure silicon to build on, couldn't we just pour that 1420-degree melted silicon into a flat mold, kind of like baking a cake or casting a bronze sword?
I mean, it's a totally logical thought, but if you pour it like cake batter, you lose control of the atomic structure. As that liquid silicon cools in a mold, the atoms will start crystallizing in countless different places at once.
Oh, so they don't line up neatly.
Exactly. They form multiple, distinct, overlapping crystal structures that eventually crash into each other as they harden. You end up with what is called polycrystalline silicon.
So all those different crystal structures crashing together would create essentially a microscopic traffic jam.
A catastrophic traffic jam, yeah. The borders between those different microscopic crystals act like physical roadblocks for electrical current.
And we need electricity to flow smoothly.
Right. We need uniform, perfectly predictable electrical properties across the entire surface of the chip. So by pulling one single seed crystal very slowly out of the melt, every single atom of the molten silicon aligns itself perfectly with the structure of the seed.
So it forms one continuous, unbroken geometric lattice.
Exactly. That perfect lattice ensures that an electron will behave the exact same way, no matter where it is on the chip.
Which makes sense, because the structures we're about to build are nanometers wide. You can't have an electrical roadblock in a wire that's only a few atoms thick.
No, you'd have a dead chip.
So we pull this giant, perfect, glowing cylinder of pure silicon out of the furnace. But a giant cylinder doesn't fit in a phone.
Right. So we have to slice it. We use these microscopic diamond wire saws to
Yeah.
slice that massive ingot into incredibly thin wafers,
How thin are we talking?
usually about 0.5 to 1 millimeter thick.
Wow, that's brittle. And then comes the polishing. We take these thin wafers and polish them using a combination of chemicals and mechanical grinding until they reach an atomic smooth mirror finish.
Atomic smooth is the key phrase there. which means the surface variations are literally measured in individual atoms.
That is insane.
It is. But again, thinking about the scale, if you're building a transistor that is only a few nanometers across, a microscopic bump on the surface would be devastating.
Like trying to construct a skyscraper on top of a jagged mountain peak.
Exactly. It has to be flawlessly flat.
So we have this beautifully pure, perfectly flat, atomic smooth canvas, but you can't just take a Sharpie to a mirror to draw your circuits. How do we actually start drawing wires and switches on something this impossibly small?
Well, this brings us to the front-end fabrication, where the actual transistors are born.
Yeah.
And ironically, before we draw anything, we have to intentionally rust the perfect silicon we just created.
Rust it. Oh, wait, you mean oxidation. We take the silicon wafer and heat it inside a high-temperature furnace filled with pure oxygen gas.
That's the trick. The oxygen reacts with the exposed silicon to grow a thin, incredibly uniform layer of silicon dioxide over the entire wafer.
Which is essentially high-quality glass, right?
Pretty much. And this oxide layer is really the unsung hero of the microchip. It serves as an electrical insulator, and it provides physical protection during the harsh manufacturing steps that are coming up.
And it also acts as a gate oxide, right?
Yes. Most importantly, it's the actual physical barrier that will help control the flow of electricity inside the transistor later on.
Okay, so once we have that crucial oxide layer, we do a photoresist coating.
Right. We have to coat it.
We literally drop a liquid chemical called a photoresist onto the center of the wafer and then spin the wafer at thousands of revolutions per minute.
Yep. Spinning it that fast uses centrifugal force to spread the liquid out.
Into an ultra-thin, perfectly even film across the entire surface. And that sets us up for the single most critical step in the entire fabrication process, which is photolithography.
It's definitely the make or break step.
I was trying to visualize this, and the best way I can describe it is that we're basically printing billions of tiny blueprints all at once. Here's where it gets really interesting, because we're literally using invisible light as a physical tool to draw these microscopic patterns.
Yeah, what's fascinating here is how optics bridge the gap between human design and the nanoscale reality.
How so?
Well, you have this wafer coated in a photoresist, which is a chemical designed to be extremely sensitive to ultraviolet light. Then you place a mask over it.
And the mask is basically a massive stencil containing the incredibly complex layout of the microchip circuits. But the mask itself isn't nanometer-sized, right? Like, humans and our machines can't easily manufacture a stencil with holes the size of a few atoms.
You've hit the nail on the head. The stencil is actually quite large. We shine a highly focused, intense beam of UV light through that large mask.
Okay.
But between the mask and the silicon wafer, there is a series of incredibly complex, perfectly ground lenses.
So as the light passes through the mask, the lenses bend and focus the light rays, right? Shrinking the projection of the pattern down by orders of magnitude.
You got it.
Oh, wow. So you project a macro-sized stencil through a magnifying glass in reverse, and the light that hits the wafer is shrunk down to the nanometer scale?
That is exactly the concept. Wherever the focused UV light hits the photoresist on the wafer, it triggers a chemical reaction.
So the light is changing the chemical structure.
Yeah, exactly. The bonds in the photoresist either weaken or strengthen depending on the specific chemical used. After we expose the whole wafer, we wash it with a chemical developer.
Very similar to developing a photograph in an old-school darkroom.
Yeah, identical principle.
The developer dissolves away the areas of the photoresist that were exposed to the light, but leaves the unexposed areas perfectly intact.
And just like that, the digital blueprint designed by engineers on a computer has been physically transferred onto the silicon wafer as a complex microscopic chemical maze.
It's an incredible feat of engineering. But drawing the blueprint on the photoresist is only half the battle, right? Because right now, the pattern is just sitting in that temporary chemical layer on top of the wafer.
Right, it's just a stencil at this point.
So to make the circuit real, we actually have to carve those microscopic blueprints deep into the physical silicon dioxide itself.
And for that, we move to etching. We have those areas where the developer washed away the photoresist, leaving the underlying silicon dioxide exposed to the elements.
And now we introduce an etching agent. This can be wet chemicals like extremely harsh acid baths or something called dry etching, which uses plasma.
Yeah, dry etching is really the standard for these tiny scales. We introduce gases into a vacuum chamber and hit them with a strong electromagnetic field.
Until they turn into a glowing, highly reactive plasma.
Exactly. And that plasma acts like a microscopic sandblaster. It violently eats away at the exposed silicon dioxide,
Right.
cutting deep, precise channels into the wafer.
But wait, it doesn't eat through the photoresist that we left behind during lithography.
Right, the remaining photoresist acts as an impenetrable shield.
Oh, okay.
So the plasma is only carving away the exact shapes dictated by our shrunk-down blueprint. Once the etching is complete, we chemically strip away that remaining photoresist.
And we are left with the physical circuit shapes permanently carved into the oxide layer. Okay, so we've successfully carved the physical shapes,
Yeah.
but pure silicon, even when carved perfectly, doesn't actually conduct electricity very well. In fact, its perfect crystal structure makes it a pretty terrible conductor.
It's true. It needs some help.
So to turn these carved shapes into actual switches, we have to do something called doping, or ion implantation.
Yep, doping.
We take an atomic gun and literally shoot specific ions directly into the exposed silicon lattice. We use boron to create what's called a p-type region, and phosphorus to create an n-type region.
And bringing those two regions together forms a PN junction, which is the heart of the transistor.
But I have a big question here. Why boron and phosphorus? What is it about shooting these specific elements into the silicon that turns a microscopically carved rock into a functioning computer switch?
Well, this raises an important question because it gets to the very definition of a semiconductor. Remember how we talked about that perfect, unbroken geometric lattice of the single crystal?
Yeah, the one without the traffic jams.
Right. In that pristine state, every silicon atom is perfectly bonded to its neighbors. All of their electrons are locked tightly in place.
So they can't move.
They simply cannot move. And if electrons can't move, you have no electrical current.
So it's essentially acting as an insulator at that point.
Precisely.
Yeah.
But if we violently shoot boron atoms into that perfect lattice, we disrupt it. You see, boron has one less outer electron than silicon does.
Oh.
So when a boron atom forces its way into the crystal, it creates a hole in the lattice where an electron technically should be. We call this a p-type region, for positive, because of the missing negative electron.
Okay, so I like to think of the boron creating an empty parking spot for an electron. It's an open space just waiting to be filled. So what about the phosphorus?
Phosphorus is the exact opposite. It has one extra outer electron compared to silicon.
Got it.
When we fire phosphorus into the silicon, it bonds with the lattice, but it has this extra electron left over. We call this an n-type region for negative, because now there is a free wandering electron that isn't locked into the crystal structure.
So on one side, you have an empty parking spot violently pulling nearby electrons toward it, and on the other side, you have a wandering electron desperately looking for a home.
And they naturally want to rush toward each other.
Makes total sense.
When you place that p-type region right next to an n-type region, you create the PN junction. But remember that gate oxide layer we built earlier?
Right, the glass barrier.
By applying a tiny electrical voltage to that gate, we can create an electromagnetic field that essentially lifts a microscopic floodgate.
Oh, so we control the flow.
Exactly. We can control exactly when those extra wandering electrons from the N side flow across the junction to fill the empty parking spots on the P side.
And if the electricity is allowed to flow across the junction, the switch is on, registering as a 1 in computer code.
Yep.
If we remove the voltage and stop the flow, the switch is off, registering as a 0.
That atomic level dance of electrons is the fundamental building block of all modern computing. And we just built billions of them simultaneously on a single chip.
It is honestly mind-blowing when you trace it all the way down to the wandering electrons. But here's the thing. We now have a microscopic city of billions of individual transistors sitting right next to each other.
Right, a very crowded city.
But a bunch of isolated switches don't do anything on their own. How do we actually wire up this nanoscale metropolis so they can talk to each other?
We have to build the roads and the power lines. We do this through thin film deposition and metallization.
When I was looking into how we deposit these materials, I kept seeing CVD and PVD, which stand for chemical vapor deposition and physical vapor deposition, and frankly, it sounds completely sci-fi.
It feels like magic, honestly, but it's incredibly precise chemistry. We can't just pour melted copper over something this small.
No, obviously not.
Instead, we place the wafer into a vacuum chamber and introduce highly purified gases. Let's look at CVD. When those specific gases meet in the heated environment right above the wafer, they undergo a chemical reaction.
Okay.
The byproduct of that reaction is a solid material that literally rains down onto the wafer.
So you're basically creating a microscopic storm inside a vacuum chamber where it rains down a new material atom by atom.
Atom by atom, yeah. building up a flawlessly even layer of insulators, polysilicon, or whatever dielectric material the circuit needs at that specific level.
And then comes the metallization, where we use similar processes to deposit incredibly thin layers of copper or aluminum wiring to interconnect all of these billions of transistors, forming the complete massive logic circuits. But here's where the sheer scale of this really terrified me. We don't just do this once. Modern chips are completely three-dimensional.
Oh, absolutely. They're stacked.
So to wire billions of transistors together, you have to stack layers of wiring on top of each other. The cycle of spinning on photoresist, shrinking the blueprint with UV light, etching with plasma, and depositing metal. It's repeated 20 to 50 times on a single chip.
They're basically microscopic skyscrapers. The wiring complexity is equivalent to the entire street grid of New York City, stacked on top of itself 50 times, but shrunk down to the size of your fingernail.
But wait, if you're applying liquid photoresist, aligning a tiny mask with reverse magnifying glasses, blasting it with plasma, and raining down metal 50 different times at a nanometer scale,
Yeah.
doesn't that mean you have 50 different chances to misalign a single layer by a fraction of a hair and utterly ruin the entire multi-billion transistor chip?
Your anxiety is entirely justified there. And it is the exact reason why microchip fabrication plants, often called fabs, are the most expensive, complex, and tightly controlled facilities ever built by humanity.
Because of the margin for error.
Exactly. If layer 37 is misaligned by a margin so small you couldn't see it with a traditional microscope, the copper wire simply won't connect to the transistors on layer 36.
And the circuit breaks.
The circuit breaks and the entire chip is garbage.
So how do they prevent it?
By controlling the environment to a degree that almost defies belief. These clean rooms are billions of times cleaner than a hospital operating room.
Billions of times.
Literally. A single speck of dust or a stray flake of human skin dropping onto a wafer during layer 37 is like a meteor crashing into a city. It wipes out thousands of transistors instantly.
That is terrifying.
Right. The factories are built on massive shock absorbers, so that a truck driving by outside doesn't cause a nanometer vibration that misaligns the UV light. The temperature and humidity are locked in place, all to ensure that when they repeat this brutal cycle for the 50th time, the alignment is mathematically perfect.
So we've just built a 50-story microscopic skyscraper out of glass, metal, and doped silicon. But pure silicon is incredibly fragile. If a speck of dust hitting it during manufacturing is like a meteor, what happens when it leaves the clean room?
It wouldn't survive long.
Right. If we expose that multi-billion transistor metropolis to the real world, it would be instantly destroyed. How do we get it out of the lab and into a laptop?
That is where we transition to the back-end processing, basically boxing it up for reality.
Okay, so the first thing we do is wafer testing, or the probe test. We use actual microscopic electrical probes to test each individual chip while they're still connected on that massive silicon wafer.
Got to make sure they actually work.
Exactly. Any faulty chips, maybe the ones where layer 37 didn't quite line up or a rogue atom got in, are permanently marked to be discarded. Then comes dicing.
Right, the dicing.
Where we take that beautiful mirror finish wafer and brutally slice it into small individual squares called dies.
And at this point, the die is the actual functional microchip.
Right. But we aren't done. The final step is packaging. We place that fragile silicon die into a protective plastic or ceramic package. We use a wire bonding process or a flip chip method to connect the tiny circuits to the package, and we add pins or little metal balls to the bottom.
Yep.
Finally, we run it through final testing to check its speed, power consumption, and reliability. So what does this all mean? Why is this packaging step so intensely elaborate with all these balls, pins, and gold wires? Isn't the chip essentially ready to compute the moment it's diced from the wafer?
Well, if we connect this to the bigger picture, you have to realize that packaging is entirely about bridging the gap between the nanoscale and the macroscale and ensuring survival.
It's if the bare silicon die is basically naked.
Exactly. If you exposed it to room temperature humidity or the physical pressure of snapping it to a motherboard, it would short out or shatter instantly. Yeah, so the plastic or ceramic package acts as a suit of armor. But it also solves two massive engineering problems. First, physical electrical connections.
Because the transistors are so small.
Right. The transistors and wires inside the chip are nanometers wide, but the wires on your computer's motherboard are millimeters wide.
Right, you can't just plug a massive copper cable directly into a circuit that's the width of a virus.
You'd crush it. So the wire bonding or flip chip connections inside the package act as a physical bridge. They step up the microscopic connections on the die to the larger metal pins or balls on the outside of the package.
Which then connects safely to your device.
Exactly. And the second massive problem is heat.
Because you have billions of switches turning on and off billions of times a second.
Right. The friction of those electrons moving creates an intense amount of thermal energy. If that heat has nowhere to go, the tiny silicon structures will literally melt themselves into a puddle in a matter of seconds.
That would be a very expensive puddle.
Very. So the packaging is designed with specialized thermal interface materials to aggressively pull heat away from the silicon die and dissipate it out into your phone or computer's cooling system. Without that elaborate packaging pulling away heat and bridging the physical connections, the brilliant nano-engineering of the fab is entirely useless in the real world.
And that takes us to the end of the line, final use. We've traced this absolutely incredible journey. We started with raw silicon extracted from common sand. We purified it to 9 nines. We pulled a single continuous crystal out of a 1420-degree pool of molten rock. We sliced it, polished it to an atomic mirror, oxidized it, and spun photoresist onto it.
It's quite a list when you say it all at once.
It really is. We use massive lenses to shrink a blueprint down, painting it with invisible UV light. We blasted it with plasma, shot it with boron and phosphorus to create billions of wandering electrons in empty parking spots, and rained down microscopic copper wires in a vacuum chamber 50 times in a row.
All without a single speck of dust.
All without dust. We chopped it up, gave it a suit of thermal armor, and tested it. And where does it go? It goes right into the hands of you, the listener. These chips are sitting inside your smartphones right now.
Everywhere around us.
They are powering laptops, running massive AI server farms, calculating routes in your cars, orbiting the Earth in satellites, and regulating life-saving medical devices. Everything we do in the modern era relies on this extremely precise nanotechnology.
It really is an absolute triumph of human ingenuity. But looking at all these processes, how we polish silicon to be atomic smooth and build billions of transistors at the nanometer scale, it leaves us with a profound realization about the future of technology.
How so?
Well, we've spent decades shrinking these blueprints down, following Moore's law, making devices faster, cheaper, and smaller. But we are already at the point where we are manipulating individual atoms of boron and phosphorus to make these switches work.
Because a transistor can only get so small before a single atom is the size of the switch itself.
Exactly. And that is the wall we are rushing toward. Eventually, the fundamental physical laws of the universe itself will become the ultimate bottleneck.
Wow.
When we literally cannot shrink the physical blueprint any further, when an atom is the absolute limit of our canvas, how will the digital world evolve? How do we continue to build faster, more powerful computers when the laws of physics simply say no smaller? It's the ultimate engineering hurdle of our generation, and it's a puzzle we have to solve soon.
Something to seriously think about the next time you pick up your phone to send a text or, take a walk on the beach. Thank you so much for joining us for this deep dive. It's been an absolute blast unpacking this with you. Until next time, keep exploring.